In this video, we're going to look at the cyclopropanation reaction. And this is similar to the epoxidation in that we're adding something across the double bond, but instead of an oxygen, we're adding a carbon to form a cyclopropane. Here's our basic setup for a cyclopropanation reaction. We have an alkene, and we have this CH2 with a lone pair. This is called a carbene. It's a very reactive and unusual species. It's an uncharged carbon with 6 electrons. So it's electron deficient in that it lacks an octet, yet it has a lone pair, so it's nucleophilic. So it's kind of both a nucleophile and an electrophile in one. In the presence of a carbene, the double bond is going to react with it, and the way this happens, this carbon wants electrons, so we can use the pi bond and add electrons to it, but at the same time, it has a lone pair, and that lone pair can come and add to the other carbon. So let's put this pi bond in red so we can track where those electrons go. When I draw the product of this, I'm going to have one bond to the CH2 and a second bond to the CH2. Now, usually we would just write this kind of like this, so we don't have to draw the CH2 in. Also, like epoxides, both of those bonds must be in the same direction. So both bonds are syn to one another. We'll do another example in a minute where we consider all of the stereochemistry. But I do want to talk about this carbene because this isn't something you can just keep in a bottle and take off of the shelf. It's highly reactive, and it's something you need to prepare just prior to your reaction. And the best way to do this is known as the Simmons-Smith reaction. And what this reaction does is it uses diiodomethane. So it's CH2I2, and we add this copper and zinc mixture to that, and that forms the CH2 carbene. The actual mechanism for how this copper zinc mixture removes the two iodides to give you the carbene, that's a little bit beyond what we need to talk about. So just know if you mix these two reagents together, you're going to get the carbene. So now let's look at another example where we have the conditions written over the arrow and we'll predict the products. Here we have an alkene, and we're subjecting that to the Simmons-Smith conditions. We already have one chiral center in the molecule, and the carbene will add across this double bond, but like we've done in many other cases, it can add from the front, and it can also add from the back to give us two different stereoisomers. So if it adds from the front, leave the phenyl as it is, and we're going to add that across the double bond, and I'll put the CH2 as a wedge. Kind of like that. If we add it from the back, again, the phenyl group stays where it is, but now we'll put that CH2 added as dash groups. So here we have our original chiral center. We formed two new chiral centers in the molecule, and this gives us a pair of diastereomers.